Hi everyone. So this is basically a retake from the example video, but we're just given a little more information. So now we know the speed every 1 second instead of every 2 seconds, which in some ways actually makes the arithmetic a little bit easier. So now we're just going to make our very best estimate for distance traveled, which means we'll use every single 1 second time interval. So we're going to go 0 to 1, 1 to 2, 2 to 3, 3 to 4, and so on. Okay, so if we want to get our upper estimate, we can say that the car travels at most, and we know that, let's see, okay, so for the first 1 second time interval, the fastest it goes on that time interval is 100 feet per second. So the upper estimate is going to be 100 feet per second. And we're going to multiply that by 1 second. And you can get a nice little units check. You don't have to write them every time, but here we can kind of see that the seconds multiplied by the feet per second, I don't need to cross that whole thing out, just leaves us with feet, which is perfect. And I deliberately put that 1 second out in front because I'm sort of preemptively thinking about this and saying, okay, well then when I go from 1 to 2 seconds, I'm going to take my 96 feet per second, and I'm going to multiply it by 1 second as well. So if I just capture all of this in parentheses, that 1 second is distributed to everything. And in our head, we know really all that's doing is fixing units for us. So I'm going to be lazy and not write the units the rest of the way. So from 2 to 3 seconds, the max speed is 80. From 3 to 4, it's 68. From 4 to 5, it's 50. From 5 to 6, it's 40. From 6 to 7, it's 25. From 7 to 8, 15. And 8 to 9, 10. And 9 to 10, 3. Okay, so this is my calculation. And again, the 1 second, all it really does in this case, since you're multiplying by 1, is correct your units. And I did this in advance so you wouldn't have to listen to me try and do all this arithmetic. And I already forget what I got, so let me just peek really quick. I think it was 487. Yes, 487. So, okay, and the units on that should be feet. So the car traveled at most 487 feet, and the car traveled at least... and this will be very similar, but now when we go 0 to 1 seconds, we're going to take the 96, and 1 to 2, we're going to take the 80, and 2 to 3, we're going to take the 68, and if you notice, we skipped the 100, but otherwise there's the 96, the 80, the 68, so really, we're just going to take all the exact same numbers as last time, but we leave off the 100 at the beginning. Plus 10, plus 3, and then for that last time interval, so the 3 was for 8 to 9 seconds, minimum speed was 3 feet per second, and then from 9 to 10, the minimum speed is 0. So in this case, again, the 1 just fixes our units. Really all we've done is tacked a 0 on the end here and gotten rid of the 100, so we should get 100 less. We should just get 387 feet. So this means we can say a couple of things. Here, let's not write it that way. Let's say this. We could, 1, give the inequality statement, say 387 feet is less than or equal to the distance traveled is less than or equal to 487 feet. Or we can say a good estimate. So the estimated distance traveled is just the average of those two. So add them up and divide by 2. And we should get 437 feet. So both of those are decent ways to answer this. And the question either will say specifically or I'll be happy with whichever way you answer it. So if I say give an estimate, then give me that number. If it's more vague, you can just give the inequality. Oh my goodness. I kept wanting to say interval, which actually probably would have worked too. Okay, so just like last time, we can interpret this as areas. So let's see, I used blue, I'll stick with that. So for the overestimate, the difference is now just we're using 1 second time intervals. So let's see if I can make this look nice. So the first one is 100. The second one is 96. The third one is 80. And then 68. Feel free to fast forward if you don't want to watch me do every single one. We can look up at the table to figure out exactly where these cross, but we're getting a pretty good rough picture here just by making sure that the top left-hand corner of my rectangle touches the curve. So the biggest y value on the interval represents the height of the rectangle. Okay, so all of this area is our estimate of the area trapped under the curve. Oops, I'm getting outside of my, oh no, that's actually good. Okay. And if we want to do a lower estimate, it's just going to move those heights over. So let me grab purple. So now the first rectangle is going to be the shortest height in that interval. Second, third, fourth, fifth, sixth, seventh, ninth, and then the last one was completely flat. So now if we look at this area, I guess I can extend it across. Getting kind of messy. This is an underestimate of the area trapped under the curve. And just like before, when we average, you could think of that as splitting this distance between the two vertically, but actually I think a better visual for that is if you think of splitting it again diagonally. So what do I want? We'll go with pink. So if we split this diagonally, you can see that now it's still not perfect, but it's really good. It follows that curved shape much more closely than those horizontal lines at the top of the rectangle. So one way to think about that is we're using trapezoids to represent the area instead of using rectangles, which is going to do a little bit better job. Another way to say that to yourself is to say what we're really doing with the tops of those rectangles is trying to approximate the shape of this curve with little horizontal line segments. So we're trying to draw a picture of the curve, but we're only allowed to make horizontal lines, so we just do the best we can. And when we average the two, instead of having to make horizontal line, we can use any old line, which does a much better job. So going from a constant function, degree 0, to a linear function, degree 1, is going to make it a lot easier to follow the shape of the curve. And we aren't really going to get into this, but you can go into, okay, what if instead we used pieces of quadratics, pieces of parabolas? Could we do even better? And the answer is yes. You can use pieces of cubics. So you can really get into this using little pieces of polynomials to approximate the shape of curves. And the convenient thing about that is polynomials are much easier to work with than just about any other function. They're really nice and simple. Okay, so hopefully that went okay. Thanks for watching.